So yes, we looked at the basic definition of machine learning, what learning is in a vacuum, how it differentiates from artificial intelligence, how it's a subset of artificial intelligence, looking at the different types of machine learning. As I mentioned briefly, we had supervised, unsupervised, and reinforcement learning, and how supervised looks at a particular set of classes and categories, basically labels for you to put your data in that is inputted. Whereas unsupervised has no labels. You're basically relying on a well-trained model. So we looked more at supervised learning and how it's more important in that regard. It makes up about 99% of the equity and the advancements in machine learning at this point in time. The different kinds of classification, and an in-depth look at regression to record and predict continuous data, and the idea of cost and how to minimize cost, how to reduce the margin of error, how to reduce the margin of error with a model that you're training. And the way we do that, the automated method for which we do that is through gradient descent. So the higher points represent a cost function or a model that's making inaccurate statements and claims. And it's carefully moving down this gradient to where it can find a valley or a trough where it's making less incorrect assumptions, regressions, calculations, classifications. So before I begin this next activity, were there any questions that anyone had in mind about last week? And looking at the chat as well.
Is it possible for you to go to the gradient descent section like the last 3 slides?
Of course. We'll go through that now. No worries. Gradient descent is a very daunting subject that I managed to try and teach to you all. Right. Gradient descent looks at trying to minimize the cost or the error margin your AI model is making with each regression. So when we are calculating a regression, we look at the distance that each data point makes from the line that we're drawing vertically. And then we're summing them all up, squaring them so they have a positive, so that they're absolute and they're positive. Dividing them by a certain coefficient so that the resulting values aren't too big. So we can like look at them all and there's not a vast gap in between each one. And then we are basically assessing the value of the output of that cost function. Cost function, are you familiar with cost function? Yeah, it's basically having a higher cost function represents more errors being made and more inaccurate predictions being made by your model, and a lower one is what we're aiming for. So this graph here, where there is a higher point on this graph, represents a high cost function. So along these axes here, we have the two variables we're changing. So one of them will represent the gradient of our regression line. One of them represents the bias or the intercept of our regression line. I think it's important to note the mathematical aspect behind this. Has anyone here used a website called Desmos before? Desmos, it's a really good graphing tool. You can make regressions and linear graphs and better understand it that way. I'm sure we have, do we have that in our resources tab? Desmos, yeah. Thank you. So Desmos should hopefully be in our resources tab on our site that you can access. You can have a quick play around with that. I heavily recommend it. It's helpful for both mathematical fields, statistical fields, as well as machine learning and computer science.
Can you pronounce again that one?
Desmos. Shall I spell it out? DESMOS. I'll put it in the chat as well. should appear there.
This is useful for linear regression. Yeah.
It's useful for specifically graphing the regressions that you can make. So one particular way you can look at it. So this right here, we have a regression. And we have, sorry, we have a question here. Is the cost function used to check the machine learning model against the trainer data? Yes, it is. Yes. You're basically trying to find the ML model that makes the least amount of distance from the given training data that you have. So when we have less distance between each data point vertically and the line, we tend to come up with lower cost functions, and as such we move down this line. We always try to choose a point with gradient descent that has a typically high cost function, so that we can find different points in the valley where we can find different points along this landscape where the valley is the lowest, or there is a point where it doesn't go any lower. So a typical way to visualize gradient descent is that you're starting on a hill and you're making your way to the bottom. And you're looking at, so say you're on the peak, which represents a high cost function. You're looking to find the steepest descent from where you are. And once you found it, you go down from there. That represents, once you reach that point, a cost function that is lower. And there, in turn, it makes for a more accurate regression. And then from there, you keep finding where the steepest point is, and you go down steadily calculated until you reach your bottom. Now, we have 3 points, or 3 troughs, or 3 valleys, as I like to say. And as you can see, there is a global minimum right here. This represents the lowest possible cost function you can have. But let's say we started at this particular peak between A and B. You won't necessarily reach this here, this lowest point of C. So that's why it's important to run through gradient descent with different values for your gradient and your bias, and reach each peak and go down steadily from them each time. So gradient descent requires multiple run-throughs, using multiple starting values for the gradient and the bias. To then reach the bottom, several bottoms, yeah. Are there any more questions that you have? Okay, hope that helps.
Yeah, okay.
So a bit of an important thing to note from last time. If you remember, everybody, if you remember from last time, we had the example of house prices. We had an input being house size in square feet, and our output, what we're measuring, what we're trying to find, being the cost of the house. So we had one input. We had one input, X, to an output, Y. Now, what I'd like you to look at in our session today, advanced linear regression, is the sentiment of multiple features. So now we have size in square feet, the number of bedrooms, number of floors, and the age of the home in years. And now, and we still have price of the house in thousands. So what X, oh, what is this? That's not right. Now, this X can be described as a feature of the table that goes into making our output, what we're going to be measuring. Now that we have more than one input, we we are instead having one, using our example again, we have one for house size, one for the number of bedrooms, one for the number, let me see again, one for the number of floors, and one, pardon me, this is very cramped, and one for the age of the house. This represents multiple features. Now, there are many reasons why we use multiple features when it comes to making a regression. These can also be described as degrees of freedom. So when we get given data, there might actually be another field or a feature that explains more about house price, and we'll derive a different regression with a different weight and a different bias assigned to it to achieve a supervised model to predict house price. But we can actually use this collection of features together, all to derive one output for the price. They all have their own, they all actually have their own weight. They all actually have a different impact on the output of our output. So there are many reasons, again, why we like to increase the degrees of freedom with our data. One is flexibility. You can pick and choose what features you'd like to include when making a regression. You can have multiple regressions that explain different things. Another one is statistical power. Basically, just having more data to a degree is better. Not having too much to overload a model at any point, but having the right amount of features and records can provide some more valuable insight into the output that you want to receive. And with these many models, you can actually engage in what is called cross-validation, where you would look at one model, one regression, and it can actually help you explain another regression as well. Say we had one graph for just the feature of size in square feet against the output of price, and another one of number of floors with price in thousands. We can compare the two and see a correlation between the two. But now we're saying we can actually put these multiple features into one graph with multiple weights and just one bias. This is a lot to look at. I think it's more important we illustrate this slowly with a whiteboard. Does anyone have any questions so far? Dokes? Anyone in the chat? Okay. I think, yeah, so rubbing this all off now. So from last week, we're not adding particularly any new function to what we're doing. We're going to be refining our existing linear regression function, but now facilitating more than one feature. So if you remember, we had our function that factors in weight and bias of x is equal to the weight or the gradient multiplied by our input value plus an intercept, a bias. But with multiple features, each feature has their own weight. So let's say we are looking at two different features in our table and one output. Oh. We have two features, x1, x2, and we have another feature that's being added here. And with these two, features, they each have their own individual weight because they matter differently to the model. They're weight 1 and weight 2. And there's a one-to-one correlation here. So each weight is assigned to its own input variable. So we have weight 1 with input feature 1 and weight 2 with input feature 2. We don't have two biases because a bias is just, or an intercept rather, is something we shift along and it's cumulative to sort of give us a good starting point from where our data should go. So we only still have one bias. So what's changed? We now have multiple X's, multiple W's, and what's the same is that we have the same B, same bias. So as you can see here, this goes up to a table with a number of features, with n features, n being a variable. And yet this goes over it again. Wi represents the coefficient, the weight. Now this I is important to look at. I represents the index of the input feature or the weight we're looking at. So W of 1 should always go with X of 1 because that is the weight that's being assigned to that specific input feature. Anyone have any questions on that? So back to our example. Now we actually have tangible, well, enumerated values for each of our weights right here. So looking through, the bias of 80, well, the base price of a house that our model has calculated, and each of these weights. So let's start here with 0.1. For each additional square root, the price increases by £100. Notice the scaling here as well. Scalability is an important factor when we're modeling because we don't want to use values that are too large in our data. Otherwise, they become tricky to look at and to an extent tricky to compute as well. So price in thousands is important to denote here. And as such, we're using smaller values for our weights. This makes it much easier to program with. So with weight 2 representing the weight that goes with the second input feature, number of bedrooms, for each additional bedroom, the price increases by 4,000. So these numbers here will represent at the end a cost, a price in thousands. For weight 3, for each additional floor, price increases by 10,000. And this negative weight right here, for each additional year, the additional year of the house age, the price decreases by 2,000. So things that make sense, but things that we can also infer as we go on. Now, vectors are an important thing to look at here. So, so I thought you had a question. Sorry. Vectors are another key thing to look at. So we have all of these values, these input features. They can all be stored in what's called a vector. And the notation we use for this is as follows. So these are our input features. They're being stored in this, what we're calling this variable of X. This notation here is to signify that it is in fact a vector. Now, who here is familiar with the term for vectors in mathematics? Or what is a vector in mathematics? Yeah?
The direction or something? It's been a long time.
No, no worries, no worries. But yes, a vector has a direction and a magnitude. It's a movement in space from a given point. Or yeah. So if you look at the mathematical aspect, you have a movement right here. it can be looked at from two different axes. And let's say that was a movement to the right by 1 and movement up by 2. Have you got it so far? This can also, let's say this vector was called A. So A is equal to I, or 1I, but this I is silent, plus 2j. And it can also, now this vector can also be written as 1, 2. Notice how there is a fixed width. There is only, it can only be going down. There is no width dimension. There's no width factor here. It's a one-dimensional array. The key word in this is array. A vector in computer science is in effect a one-dimensional array. It has a fixed dimension of 1, but it can go for as many length as it can go for as many values as you desire. Now, because we can store each of these input values or these features into their own vector, we can store all of our weights into a variable W, capital W, with W1, W2, and W3. So we have a way to store our weights and our input variables. And as you may remember, W of 1 multiplies to X of 1. So there's something here. Like that. This can actually be computed manually and using libraries in Python. But now we have a set way to multiply each weight to each input variable. So for mathematics, we can understand vectors as objects with a direction and magnitude. So note how the values contained in this array are single file and have a fixed width. So in the context of computer science, programming, and data storage, a vector is a 1D array or one-dimensional array used in more mathematical applications. So from this notation here that I slowly wrote out, we have our two vectors, X and W. And instead of having to write out, as I did previously, W of 1 of X of 1 and W of 2 of X of 2 up until we reach the end in our bias, that's well, taxing on your hand, if anything. So we actually can write it out with dot notation. So we have these two vectors being multiplied by each other. This notation of vector W multiplied by vector X is equal to our weights of each individual index being multiplied by each other summed up. Who here is familiar with vector multiplication? You don't have to be, for the record. If anyone is, that can kind of sort of aid in the understanding of why this equation sort of works. You are, yeah. Yeah. I'll illustrate it very briefly again. When we are multiplying vectors, this is one vector. This is another vector. You are multiplying in the order they're given. So these two don't multiply. These two don't multiply. You're going along down the bottom. You're going along from the top down the bottom with each value. So we've got AC, or A times C right here, and B times B right here. And the same can apply with if you have X of 1 and X of 2, and W1 and W2 in those values instead. Yes. That make sense? So, oh yes. The one I just wrote right now. Oh yes, this was an example. I used just basic algebra for each one.
Not in that.
Oh.
If you go back to the slides.
Oh yes, the bias, yes. So you may remember how, let's go. Wait. This one here?
Yeah.
So this is a simpler way of writing out each weight with each input variable. The bias still remains because it's still our intercept. This will basically mark the base point from which we're going. Do you remember from last week, we had just W of x plus b. It's very similar to how you'd write it in maths, y equals mx plus c. C or b in that instance represents the intercept. Much like here, the equation at its roots hasn't changed. We're just adding more weights and more input variables. We still have a bias. So bias hasn't changed, it's still there, but now we're just adding more weights and more input variables if need be. Does that make sense? Thank you. So vectorization, basically putting them into vectors, is very useful when programming. This looks like a lot right here. So let's go through them one by one. Normally, if we wanted to write it out in a very long-winded way that's not helpful at all, you'd go weight with index 0 multiplied by x of index 0 plus weight with index 1 times weight x of input 1. It's long-winded, computationally unnecessary. You'd rather not go there. And it doesn't really account for how many features you have. See here, we have 3 different indices being used, or 3 different numbers, 0, 1, and 2. That means that there are 3 weights and 3 features. Let's say we had 10. That would require writing out 10 lines of code individually, which is wrong. With a loop or iteration, you can use a loop. So say for I in range n, so I represents numbers from 1 to the length. So I will increment by 1 until it reaches the value that is the length of this array. It will go through, multiply each weight to its input feature, and add the intercept at the very end. This looks very complex as a whole, so I'll break it down. np.array. For those in our last lab practical, you may have used the Numpy library. At the very beginning, the first thing that you run will be all of the libraries that you import. Numpy, or Numpy, I call it Numpy. Numpy, we've shortened it down to NP. It's a silly name, isn't it? We shortened it down to NP, and we've made a NumPy array with 3 values in each one. Does anyone have any questions about this loop here in particular? Okay. Now you may think this is a much easier way of writing it out than having to write out each individual weight and feature one at a time, because you're just having a loop that goes through it, and this is the entirety of the code you'll have to write. But what's being done here is a serial progression of finding your value f. This means you're going through it one at a time through each weight and each input feature and adding the intercept at the end. This is computationally unnecessary. We'll be using too much time here. Thankfully, the NumPy library also facilitates vectorization. Now, this vectorization right here uses a function called dot, and it will take your weights, your vectors w and x. It'll take your vectors, multiply them together in parallel, which is a term I'll get to much later, and adds the intercept at the very end. So the key distinction here is that with a loop, you're going through it one weight and input at a time. With vectorization, it's all done in one step, so it's much, much faster. Anybody have any questions? So yeah, just basically going over again from last time, without vectorization, each process is being done one at a time, whereas with vectorizations, they're all performed simultaneously in one step. There is a notation we use for this. We're not getting into this right now. It's a very complex form of notation that we sometimes use, but to put it into perspective, using vectorization will get us the lowest value or the fastest value for our notation for our processing speed, while using an iteration or a for loop to go through each weight and each coefficient and each input feature one by one, that can get you a much higher, a much larger value for the time being taken. So let's say we had a linear regression model with 16 features and 16 parameters. So we have x of 1 all the way through to x of 16. A thing I think I should note down for everyone here right now is the notation used here. It can be very easy to get caught up with what this truly means. So let's just this right here means x with index 1. This is not the same as x to the power of 1. These are two very different things right here. This represents a point in the vector, whereas this represents an indice, something that's being multiplied by, which is not what we're trying to find here. Does that make sense? Let's say we had, again, 16 features and 16 parameters. So that means we're going through a loop. Say we're using that loop again. We're going through the loop 16 times, and we're going to, in that loop, we have another loop going through each feature and calculating a value then. We'd actually go through the loop 16 by 16 times. So that would be 16 times 16, which is 256 times go through the loop, trying to add things to it. Whereas with vectorization, this is all updated simultaneously in one step. Now, a key thing to note about parallelism, I mentioned it very briefly. Vectorization, the vector np dot function that was used there is done in parallel. So it's a method of computing where the multiple processes in the computer, they're all working on the same task at once. This is not a key thing to note with machine learning in particular. This is just a term I think is very important to learn because it's a format for which computing is actually done. So concurrency is oftentimes the name of the game when it comes to optimizing not a model, but the program you're using to run and train and test the model. You want faster output. So having functions that sort of deliver on that can be very useful. So parallelism, yeah, is basically, let's say we have a processor. We actually having multiple processes breaking it down. So a 5-minute task would otherwise now take 1 minute because it's being broken down to 5 processes. Does anyone have any questions? Okay.